Hello everyone, I welcome you all to my APS TFD talk on how inertia and viscosity influence the drop impact forces. And in fact, in a previous talk, Detlef talked about what do we mean by these drop impact forces and gave details about the process. And this is a work that we did in collaboration with our colleagues from Tsinghua University, Bin Zhang and Kungjing Li, who you see on the figure over here, along with other co-workers. So of course, this process is controlled by different dimensionless parameters, and the one that we care about in this talk is the Weber number and the Ohnesorg number. Weber number is the inertia of the impact as compared to the surface tension of the droplet, and Ohnesorg number is nothing but a dimensionless viscosity. And we can illustrate this process in this Ohnesorg versus Weber number phase space. And we know that this process is quite relevant both from an industry point of view, that is in inkjet printing and so on, and for natural processes such as rainfall. And in the previous talk, Detlef went through this parameter space in a horizontal direction. So he kept the Ohnesorg number constant, and there we varied the Weber number. And in this talk, we are going to vary both Ohnesorg as well as Weber number. And before I do that, let me remind you of a typical result that we obtain in such a scenario. This is the drop impact process that you see right now. And all these simulations were done with an open source software called Basilisk C, which was developed by Stefan Popine and team. And in the simulation video on the right, you see that we show that log10 of the viscous dissipation rate and the velocity normalized with the impact velocity. And when we see this kind of result, what we can ask several questions, such as how does the first peak in the impact force? It depends on Weber number and Ohnesorg number. Similarly, we can ask how does the second peak depend on Weber number and Ohnesorg number, and along with the times, the different time scales associated with the process, how do they depend on Weber and Ohnesorg numbers? But in the interest of time, today I will only focus on how the first impact force peak depends on Weber and Ohnesorg number, and similarly we will do the same for the second impact force as well. Without further ado, let's dive in to the first results. So here I am showing the dimensionless first impact peak as a function of the Weber number, and this is made dimensionless using this inertial pressure force, which Detlef gave arguments about why this is the relevant pressure scale in his talk. And you can see over here that for high Weber numbers, it essentially goes to a plateau. The question is, how does this plot change when we increase the Ohnesorg number? For example, here I show you a case where the Ohnesorg number is 2 times more than that of water, and we hardly see a difference between the two plots. As you can see, the two data points are essentially on top of each other, and the same result is also repeated when we increase the Ohnesorg number to roughly 100 times that of water, and then even then the first impact peak hardly changes from its value of that of water. And so we can conclude that since the first peak is independent of Ohnesorg number, as long as we restrict ourselves to these small Ohnesorg number limits. And then, of course, the question would be why that is so, and I will try to answer that with this slide. So here I'm showing you four different cases. The two on the left is at Weber number of 40, and two on the right is at Weber number of 2. And both of these I show you for an Ohnesorg number that is equivalent to that of water, and one that is 40 times more viscous than water. And for the high Weber number cases, I show this inertial this pressure, which is normalized with the inertial pressure. And for low Weber numbers, I show that the same gauge pressure normalized with the capillary pressure, and these two are the relevant pressure scales in this process. And you see that for high Weber numbers, the pressure inside the droplet, particularly at the region of impact, is essentially equal to this inertial pressure, and the relevant length scale is of course the diameter of the droplet. And for a low Weber number impact, the pressure inside the droplet barely changes from its capillary pressure value, and we see that both of these scenarios are essentially independent of the Ohnesorg number, even if the difference in Ohnesorg number is by a factor of 40 over here, but these two values are almost the same, and hence in the limit of low Ohnesorg numbers, the first impact peak is independent of the Ohnesorg number. So that's the first part. But what happens if we go to even higher Onizog numbers? So if we increase the Onizog numbers to a very high value, for example, so that would be, let's say, in this parameter space, we can go to Onizog numbers of much of which are relevant for inkjet printing and other applications. For example, we can keep this Weber number fixed at 10, and then we can sweep this parameter space in the vertical direction. That is what I'm going to do here. So in this plot, the y-axis shows the first peak F1 normalized with the inertial pressure force as a function of the Onizog number. And we see that for low Onizog number, it goes to a constant value, which is the same plateau that you saw in the previous slides. But however, for large Onizog numbers, the first the first peak in the impact force increases with Onizog number. And to rationalize this, I'm showing you three videos over here. One for something which is 4 times more viscous than water, then one that is at Onizog number of 0.5, and another which is an Onizog number of 5. So what we see here is that for low Onizog numbers, first of all, the dissipation is predominantly in the rim of the droplet as it impacts, and it's also more in the region which is connected to the surface, and it's less as you go in the bulk of the droplet. Whereas when we go to high Onizog numbers, for example, Onizog number of 5, the viscous dissipation happens entirely inside the droplet, and this is how we can explain this increase in the first impact force peak with Onizog number, because the momentum of the droplet is fixed. However, for the first for the high Onizog numbers, this momentum is dissipated, or this energy, the initial kinetic energy, is dissipated as soon as the droplet hits the surface. So in a very short time, whereas for low Onizog numbers, we still there is a finite time in which this initial kinetic energy needs to be dissipated. As a result, the time of impact, like the inertial shock, decreases. However, the momentum of the droplet is obviously the same, because we are looking at these cases at the same Weber number, and which means that if that the force of impact between the drop and the substrate, that should increase, because the impulse is the same, the time goes down, and hence the force increases. And this trend is quite robust. So even if we increase the Weber number, let's say to a value of 20, we still see the same increasing trend, which continues for Weber number of 30 as well as for 50 and 100. And once again, for Weber number of 100, if I show you two cases, one for Onizog number of 0.5 and another for Onizog number of 5, you really see this huge difference in where the viscous dissipation is and how long does it take for the system to dissipate this energy. So for high Onizog numbers, it really is almost instantaneous, and as a result, which leads to this high sharp increase in this first impact peak. And then, of course, we since it's a log plot, we do see that there is a scaling law. For example, this dimensionless first impact force varies with Onizog number as a square root of Onizog number. We have some ideas of how to explain this this dependence, but we don't. We are still working on it, so we don't know it for sure. And if you have some ideas about it, or if you want to discuss it, please feel free to drop by and have a chat with me about this. Okay, so now that was the story about the first impact peak, but what about the second impact peak that we also notice in such a process as the drop recoils off the surface over there. So for example, for water, we know that the scenario looks like this, which Detlef discussed in his talk, and can also be found in our recently published PRL. And here I chose to delete or to remove the data points associated with the splashing regime, which would have come over here, because for high Onizog number, that's not really relevant. So now we are going to change Onizog number for this case. And before we do that, let's first look at the case which has the highest peak in the force, which is this one over here. And if you remember, this is the case of a singular jet, where a bubble is entrained inside the droplet, and this high peak in the force is really a reminiscent of a hydrodynamic singularity that occurs when the capillary waves converge at the apex of the droplet at precisely the right way. So it's really a resonance which occurs at Weber number of 9. So what happens when we increase the Weber number from, let's say, that of water to something that is only 2 times more viscous than water? So immediately what we see between these two processes, that the impact process pretty much looks the same. However, there is no more bubble that is entrained. Let me play this video once more. And you can really see that if I were to show you these two videos side by side, then the only difference between them is that on the right, we don't have this bubble. So this convergence of the capillary waves is not as sharp as that in that of water, which we actually see when we look at the plot at the plot of the force. So you can see over here, as we look at the dimensionless second peak as a function of Weber number at an Ohnesorg number, which is twice as viscous than that of water. Almost all of the other data points over here lie on top of each other, except when we go to this region of singular jets, where the second impact peak is now diminished, and that really occurs because of this disappearance of the bubble that was previously entrained inside the droplet. And now what happens when we increase the Ohnesorg number even further? So now let's say if we go to a case which is 20 times more viscous than water, then we see that this sharp increase in the second peak, which was second force, which was over here, it simply disappears, and we get a line which just we get a dependence which simply goes down and then goes to a constant value. And that we can see also in the video over here. So these two cases you have already seen, which is water and twice as viscous as water. And now I also show you a case which is 20 times more viscous than that of water. And we can really see that for the Ohnesorg number of 0.05, which by the way is not that high in terms of the Ohnesorg numbers that we proved in the previous part of this talk. However, even for such small Ohnesorg numbers, the second peak goes down, and that's because the singular Worthington jet that was formed for water and for small Ohnesorg numbers just disappears as we increase the Ohnesorg number. And to further emphasize on this point, we are showing you the cases or the shapes of these droplets at the time of second peak. So these are all taken at time t2, and this you can see over here that for water there was this singular jet that led to not just a very high viscous dissipation in this regions around the axis of symmetry, which is also repeated for higher Ohnesorg numbers. However, immediately for a slight increase in Ohnesorg number, first the bubble disappears, and then the jet also vanishes as we go to Ohnesorg number of, for example, here 0.01. The jet is no longer the singular jet vanishes. That leads to this decrease in the second peak, which we saw in this plot over here. Now, what happens when we increase the Ohnesorg number even further, and then we see a further decrease in this force like that, and we are still working on how to explain these variations in the slopes as we look at this force as a function of Weber number. By the way, as we go to Ohnesorg numbers of higher than 0.2, let's say if you go to Ohnesorg numbers of 1, then the drop cannot bounce off the surface anymore. And then that means that the second peak also disappears, and we don't see it anymore. So for the second, is to probe the second peak, we are restricted by this limit of superhydrophobicity that disappears for high enough Ohnesorg numbers. So with that, I come to the summary of my talk. So first, we show that, okay, once again, we have an excellent agreement between experiments and simulations. And the first impact peak is independent of Ohnesorg number for small Ohnesorg numbers, and for high Ohnesorg numbers, it shows a power law behavior, which we are trying to decipher now. And then another striking feature of increasing Ohnesorg numbers is that the singular jet that was the reminiscent of a hydrodynamic singularity of converging of capillary waves simply disappears on increasing Ohnesorg number. And of course, all of this hints at is this Ohnesorg number influences both the second peak quite a lot, as you can see in this plot over here. And with that, I thank you for your attention. And if you have any questions, please feel free to find me and have a chat, or you can also send me an email, and I would be happy to reply to your questions. Thank you so much.